Okay, so we are moving on to an introduction to STAN. I brought my STAN cup for today. Oh, it's not. Oh, here you go. You can see it. Very proud of it. I like to have my coffee out of my STAN cup. Why would you use STAN and not continue with BRMS? That's a good question. I would say whenever you can work with BRMS, just do it because it makes your life much easier. There's nice functions associated with it for hypothesis testing, for predictions, and so on. I advertised Bayesian statistics as a 3D printer, which means it kind of can build all kinds of models in a very flexible way. But I must admit, I wasn't 100% honest there, because sure, BRMS is a toolbox. It's not a 3D printer. It's close to one, but it's a very big toolbox. But however, it is limited to kind of all that kind of models that are available in BRMS. So if you have a statistical problem or you write down some statistical model which cannot be fitted into this framework of BRMS, then there's then you have no other option than to code this model yourself. And this can be done either in STAN or nowadays also in Nimble. But here we are sticking to STAN because BRMS also uses STAN, and I'm staying in this framework now. So what is STAN? Let's look at some history again. I mean, statistics has a quite long history, but it only, I would say, took off practically beginning of the last century, and it took another 50 years until the first algorithm was kind of proposed at all. However, they weren't used. This was, I guess, for applied statistics, this was a niche topic, and only about like beginning of this century, computational tools became available. Classically bugs and jags, which kind of paved the way for everything afterwards. Then now we have STAN, and especially these nice packages that help to communicate with, or that automatically generate STAN models. And so the algorithm of MCMC was, I think, developed in like 40s and 50s. But it was just an algorithm on paper, and they mathematically proved that it converges at some point, but programming environment that did the MCMC efficiently for any kinds of models were developed only like a bit more than 20 years ago. Bugs is called B is, I guess, something for Bayesian. GS is for Gibbs sampling. Gibbs sampling is a special MCMC algorithm. JAX was the update of bugs, is called just another Gibbs sampler. And STAN is not an acronym. STAN is named after a person. Okay. And so this was Stanislav Ulam. It was, I think, Hungarian mathematician who emigrated to the USA. He was a mathematician, nuclear physicist, and computer scientist, and he was majorly involved in developing Monte Carlo methods. But he was also involved in the Manhattan Project, so working on the atomic bomb as well. So there is a biographical movie if you're interested in his life. It's called, I think it's a classical Hollywood movie, Adventures of a Mathematician. I watched it a couple of years ago. I don't think it's particularly well made. So it's not Oppenheimer, right? It's not a movie event, but if you're interested in his life, you can have a look there. But what is STAN? So STAN, the program was started so about 15 years ago at Columbia University. I think it's New York, right? Columbia University, think so. Yeah, by Andrew Gellman. Yeah, written in C++, so very fast programming language. And it is using some kind of Hamiltonian Monte Carlo. Hamiltonian Monte Carlo is a very efficient and interesting case of an MCMC sampler, because it kind of, if you have like this posterior, which maybe look like a Gaussian function for each of the parameters. However, it's multivariate, right? So it's a multi-dimensional shape in like 10 dimensions, because we have like 10 parameters. And MCMC can very efficiently move to the good regions of this posterior if you include not only the calculation of the posterior, but also its derivatives. So its gradients with respect to the parameter, or even the curvature. However, kind of mathematically deriving all the derivatives is a very cumbersome task. So they started to use automatic differentiation, which is a very powerful mathematical and computational tool, which for any function which is in form of a code can automatically generate mathematically correct derivatives. So it can kind of make derivatives of code. So this is very efficient. And nowadays it's adopted not only in the natural sciences, but also in, for instance, social and political sciences, the health industry, medicine, and marketing tools. So it's available for all operating systems, but not only for R, but also for Python, for Julia, and so on. So it's very versatile. And what we are using are just front ends for our computing environment, like R, that allow us in our kind of familiar computing environment to communicate or to start sampling with the C++ code, which is doing all the heavy work for us. So this is the general workflow. We usually start it here. So we just have to write a model formula. We put it into some function of the brms package. I think I never said what brms is for, right? It's an acronym for Bayesian regression models in STAN. So this automatically writes some STAN code, and it automatically calls the R package to hand this over to some compiler, and then STAN does the MCMC in this very fast programming language, C++. Okay, now we move on to here. So today we will learn how to write STAN code ourselves, but we stay completely in the R environment. We don't have to go to C++. Everything can be done in RStudio. So we have to write STAN code ourselves, and we have to use some function of the R package to work with that. So what is STAN code? STAN code can exist in two versions. So either you just write this in your R script and save it as a text object. So with the two parentheses here, it is just saved as a long text file. Or you can so no, not text file. So this is an actual variable. So it's an object in R, which is just a character string. Or you can write this in an own text file. And if you save this as a .stan file, you can also easily work with this in RStudio as a separate file. And the advantage is that you get code highlighting. So this here is much more pleasant to look at than this. I only recently, a year ago, started using STAN files. Before I was just writing this, and I have written so many green lines of code but this is much more comfortable. So what is Stan code? It is actually a direct translation of the statistical model. So a statistical model includes data. So here I have X as a predictor, Y as a response. Think of like X is latitude and Y is the average tree height. So you have some priors. I usually would write the model first before writing down the priors, because if you write down the model first, you know what parameters you are using. But I'm using this in this other order now to see to show that this is kind of the same as in the Stan code here. So we have a deterministic part and a stochastic part. This classical linear regression has 3 parameters, A, B, and sigma, and we can specify priors for all of them. So all of these blocks are represented in the Stan code as well. So we will go through each of them separately in a second. So there's always 3 blocks: data, specifying the data format, and then specifying all the parameters, and then specifying the actual model. There's other blocks available, but we won't use them for now. For instance, functions. You can write very long models with very specific kind of process-based whatever computations, and you can define functions there, for instance. The code itself, I mean, this here is the main part. This is just declaration. So this is the actual coding part. Looks similarly to R, but not always. Especially vectors and arrays, they are a bit different, especially the declaration. And they must be declared. So this is typical of other programming languages like C or C++. There you always have to declare all the variables. So you declare the format and also the size. Then each command has, or each operation has to end with a semicolon. And one difference to R is that if you want to write comments, you're not using this symbol, but you're using the double slash, which is also the same in C. Okay, so let's go through these 3 blocks step by step. First of all, the data block. I have to specify the number of observations, and then I have to specify what is the predictor and what is the response here. You can name them here as you like, right? So this is just here for the simple linear regression, I just called them X and Y. You can also give them meaningful names which correspond to your actual data. For instance, X would be latitude and Y would be height, tree height or whatever. Yeah, so you can have either integer or real types. So integer is just 1, 2, 3, 4, and real is a continuous variable. Vector is always of type real, so vector of length n includes like n continuous quantities, so each predictor value x here. If your response is integer, for instance, for like if you have count data and you want to use a Poisson or binomial distribution, then you have to specify also that the response is count data. So you have to specify that it is integer, and you can do this by defining an array of length n which contains integer values. And otherwise, Stan will not be able to calculate probability density values for this discrete distribution like binomial or Poisson. Second, yeah, you should know what are your parameters in the model. So parameters in Stan all have to be continuous. So there are no integer parameters. There is some workaround to do this, but it's kind of complicated, at least for me. I never did it so far. So here we are dealing with continuous parameters only so far. Yeah, so these are the parameters which are sampled. So they are saved and recorded in the MCMC process. You can specify boundaries here, but my advice would be only to use hard boundaries when they are necessary. For instance, a standard deviation cannot be negative, so you should include a lower boundary. For all the other parameters, setting hard boundaries, if I want to kind of narrow down this search space for these parameters, I would rather do this with a prior than with a hard boundary. So Stan is a programming language, and you can run this from different environments, right? So you would always write the same Stan code, right? So the same Stan code can be run on different platforms. We just use R or RStan. That's the R interface to Stan because we are used to working with R. But if you prefer, you can also do this in Python or whatever, in Julia. The Stan code itself is the same for all of these languages. So then we define the model, and here we define the priors and also the likelihood. We do a prior statement with this tilde command. This specifies the prior distributions. Right, so it does not say, okay, I'm randomly sampling an A from the distribution, normal distribution. It says rather, for each kind of sample in the MCNC, you will have like a specific value for A. This just means I'm calculating the probability density function of the normal one, of the standard normal distribution for the specific parameter value. Right, so in each iteration, all the parameters will have a specific value, for instance, 0.5. And this just means then in the iteration, this line just means the prior has the value standard normal distribution at location 0.5. And it can be calculated and it is added to the whole posterior density description. So this is all these three priors. So the likelihood statement, this is where you tell how the model connects to the data. And usually you will have some arithmetic operations to compute the model prediction. Here I've written this directly in the mean here. So the normal has a mean and a standard deviation. And the mean is here already expressed by the model prediction, A plus B times X. And then all the data points are normally distributed around this A plus B times X and the standard deviation sigma. So I used a vectorized form here for all the data points Y. And many operations in Stan are vectorized. But I usually, when I code, I first start with coding a for loop for all the data points. And only if that works, I maybe move on to the vectorized version. So this here just means, okay, for each data point, here, this for loop goes from 1 to n. N was defined here as the number of observations. Then each kind of response is normally distributed around the prediction, which is generated by A plus B times, and this is the kind of predictor value of the ith observation and so on. Yeah, again, I've written this in this, I've written the model prediction directly in a normal distribution, but you could also write it differently. For each data point, I compute the prediction value, which is called mu I, and then yi is normally distributed around this mean prediction and the standard deviation. So there's no right or wrong here. That's just your personal preference or coding style. Sometimes these vectorized formulas can give you speed up. They are optimized and result in faster runtimes. This can be critical if you have very long runtimes, huge model, very complex. Then you can kind of try to optimize your code by maybe vectorizing some for loops, and you might get a speed up then. So the sampling itself, the MCMC, we don't have to do anything. We just have to provide this recipe, this kind of pieces of code that allows Stan to, for each parameter value, in each iteration to compute the prior and likelihood and therefore the posterior. And the MCMC is just done automatically. We only have to provide this information here. That's all. Just as the BRMS, right? This one line, y tilde x and potentially plus a prior is just a recipe for BRMS to kind of generate this kind of Stan code, and all the sampling is done in the background. Right, so if you write in BRMS y tilde x, this means y is kind of modeled as dependent of x, then Stan will automatically generate this text. Right, so BRMS, that's what BRMS does at its core. It generates this text. I mean, not exactly this text, looks a bit different, but in principle, it just, so BRMS just takes over the work of producing Stan code for you, and it comes with additional nice functions for model evaluation. And additionally, BRMS knows what kind of model you are fitting, because you are using a certain model class, and then BRMS knows which model class it is using, and so on. Here, Stan code doesn't care about your model class. Stan code is only parameter and data goes in, and it produces the posterior density function. Not function, it produces a posterior density value. So it's just a bunch of data, and the current sample, so the current values for A, B, and sigma go in as values, and out come a posterior density value. So Stan doesn't analyze this model structure. There's nothing going on like seeing, okay, is this model linear or not, or whatever. But it doesn't have to, right? It doesn't have to. It only needs to know what is the relationship, or what is kind of, if I compute this value, this is the posterior, and this is all it needs for doing the sampling. So this is, we have to take care of this ourselves, right? I mean, by writing down the model, we kind of define implicitly what kind of model it is, but we can't use this in the output for any automated like model checking or whatever. We have to do this all manually when we're using Stan. That's a little bit of the disadvantage, and also why I would recommend using BRMS whenever you can. Sure, I mean, it's nice if you code Stan, if you want to learn Stan, and it's good exercise to code simple models in Stan yourself. But yeah, if you want to make model evaluations, predictions, and so on, BRMS comes with all these nice functions, and they are not available if you just work in Stan. Yeah, so there are some functions available in the RStan package, but it's nothing compared to all this model testing, which can be done in BRMS. So let's look at an example again. Think of the same model. It's just a linear regression, but now we fill this with some meaning. So here we have a log plant height as a response, and latitude is a predictor. And think of, okay, we already scaled this. So we have a mean of 0 and a standard deviation of 1. Okay, so this is my model. What do I have to do to let this model sample for this data set? First of all, we have to prepare the data, and not in a data frame, but in actually in a list. Because I mean, a data frame has like, I don't know, n rows and a couple of columns for response and predictor. But here we need to specify or hand over everything that goes into this data block. And here we have an integer variable n, and two vectors x and y. And since they are different data types, so n is just one value and x and y are vectors, we can't kind of put all of this in one data frame, but we have to use a list for this. A list in R is an object where you can stitch together all kinds of different variables. The only important thing is that it has to be named, and the names here have to correspond to these here in the data such that Stan can identify it. So if we had chosen here in the code to already use descriptive names like latitude for X, then we would also have to provide the name here. Latitude is equal to, and this is how Stan can identify what goes where. And then that's already it. Then you can use the stan command to both compile the model and second run the MCMC. And if you have coded this as a stan file, so for instance, my model.stan, so it's a separate file, then you call it like stan of file equals model description. Or if you didn't save this as a separate file, but saved this as a character string in R, then you can call this by stan model code equals, and then here goes the object with your character string. And you can specify some other arguments. They are kind of the same as in BRMS. How many chains, how many iterations, or if you want to, for instance, run 4 chains parallel on 4 cores, then you say cores equal 4. And that's it for model fitting. I mean, sure, it's a lot, especially this. Coding just a linear model needs a couple of lines of code. That's the kind of tedious part, but the other parts are just, just throwing the data in a named list and then already calling this with stan. We get an output. We can look at the summary statistics. This is pretty similar to what we see in BRMS. The difference is that BRMS also has all this information about the model structure. So is it a generalized linear model? Are there link functions? Is it a random effects model? As I said, Stan just doesn't know what kind of model we have. It just knows, okay, what are the parameters and what are the samples of these parameters. So we just get information about these parameters here. And then we have to kind of do the same steps for this model as we did in BRMS, but now there are just some different functions available for this. And sometimes we have to do a bit more of coding, unfortunately. But first of all, model checking. So checking with the convergence. So here you would look at the R hat value again. So this is up to a couple of digits. It's almost equal to 1. So this is fine. And you can also look at the trace plots. There are a couple of options available. I prefer to use the base plot package. And here's the MCMC combo, just gives you the same output as in the BRMS package. There are also different, I think RStan has some other functions as well. They all look pretty much alike. But this gives you the same output here as the BRMS package. But now we have a problem. I mean, not a problem, but we have to code a couple of things if we want to produce model predictions. Because Stan doesn't even know how to produce model predictions if we didn't specify this. If we didn't, I mean, we could have also have like produced another block with generated quantities where we specify which predictions we want to do. But we can also do this afterwards. I think the effort is basically identical. So the output here is just this matrix. Each column is collection of all the samples for this parameter A, which is intercept. And each line is this multivariate, this three-dimensional sample here. And if you want to do predictions, we have to do this ourselves. For instance, here, again, each sample here would create one regression line. So here I just took the first 5 samples, and for each of them, draw a line with a certain intercept and a certain slope. If we want to make the classical conditional effects plot, we have to do a bit of coding. So we are specifying the X values for which we want to produce an output. So here I just use a sequence from the minimum X. So for the minimum latitude and the maximum latitude here. So this is just a vector with some equidistant values from, I don't know, -2 to 2. And then we are declaring a matrix which is a bit like this, right? So each row of this matrix will contain all the predictions, and each column of this matrix will contain predictions at some location, right? So each column is a different location here, so different predictor value. We choose to do this for 100 predictor values. And then we will kind of make a loop. So we loop through all of these samples. And for each of these samples, we are, if we just have one of these samples, we will compute all the predictions for this one prediction or regression line. So here, this row in this matrix is computed with the sample A at row I. So we choose one of these iterations in each iteration of the for loop. And we use this intercept and the slope times predictor values to generate these predictions. So we will have a matrix where kind of each line contains basically one regression line. And then we can afterwards extract the means and the quantiles. Right, so we will have a matrix which maybe 4,000 rows. And these 4,000 rows, they specify a distribution. And we can extract, for instance, the mean and some quantiles here. And they can be used to plot here the mean line and the upper and lower credible intervals here. Okay, so this is the classical conditional effects plot, or I call it, or it's also called the fitted values, right? So here we only use the deterministic part of the model, which is this regression line. We didn't include the stochastic part of the model yet. So this is kind of the fitted distribution. It is not yet the predicted distribution. We can also produce this. So we are specifying the same values here again, but now I call this differently. I call this y-pred, but it is specified completely identically. We are doing the same for loop, but we already have calculated this mean regression or this mean prediction here, y-fit. And then we are using this y-fit, and we are drawing a random sample, and the standard deviation is given by the sigma. Again, we get a large matrix. Each row contains kind of predictions for one sample, and then we can again extract the means and also quantiles, and then we get the predicted distribution here. Right, so here we had the 5% quantile and 95% quantile. So all of this cutting the upper and the lower 5%, that leaves us with a 90% highest density interval for the data. So we suspect, or we I mean, on average, this predicted interval here should contain 90% of the data points then. Okay, so this usually we look first at the conditional effects plot. You can also do this for different predictors. If there are different several predictors, but if there's multiple predictors involved, you can always look also, or you should always look also at the residuals, because this will be just one plot, regardless of the number of predictors. And here you are making predictions for the data points. Right, so here we just wanted to make predictions for the whole range of these values on the x-axis, but now we are just using the actual data points for making predictions. So the code here is actually the same. We just choose to use xspread as just the actual observations. So here for each data point, you are producing all the predictions, and then we can extract the mean predictions and, for instance, define the residuals as the response versus the mean prediction. And then you can plot residuals versus fitted values. So classical residuals plot. In the linear model, you should always look at this residuals plot here to see again if residual standard deviation is kind of constant, or if there are kind of any suspicious structures or trends here. This should all look like a random cloud here. You can also use this for making this classical posterior predictive check plot, where you compare the distribution of the response values in the data with the distribution of the predictive response values. Again, you're using all the data points. You're calculating, you're predicting data for, you're predicting responses for all of these data points. And then you can, look at these density lines and plot them against the data. So all of these things, we unfortunately have to code them ourselves. And they are, the code is kind of different for every model because, Stan just doesn't know about your model structure. Only kind of you know about your model structure, so you have to code it yourself. What else is important? I think we're almost done here. Model comparison. Again, a bit of coding effort is necessary if you want to do model comparison, because for computing these Lu values for making model comparison, you would have to save all the log likelihood values for all the data points. Because Stan only uses prior times likelihood values, you have to tell Stan to also just save the likelihood values. And this can be done by adding another block in the model code. It's called generated quantities. And here you basically repeat the same operations you did as in the model block to just save these log likelihood values. And only then in R you can kind of extract this and use the Lu function to get these information criteria indices for model comparison. Okay, so we had, model fitting, sure, we have to code the model, sure. Actually fitting the model then is not much more effort. You just have to hand this code over to the Stan function. However, making predictions and comparing predictions to the data, you have to code yourself. And if you want to do model comparison, unfortunately, a bit of more coding in the model code is necessary. Okay, I will just show you a couple of examples of different Stan code for other classical statistical models. Okay, this is a data set we already know. So here we have occurrence of some species, yes or no, in different locations depending on temperature. So this is a logistic regression. It is defined as this linear part, A plus, so intercept plus B times predictor. And we have this logit link here. So the logit link transforms it from the response scale to the linear scale. So here we have this implicit formulation. And then the stochastic part is that the occurrence, yes or no, is binomially distributed, or we can also say Bernoulli distributed if there's just one trial around this mean prediction. However, this formulation with the link function is implicit. For Stan, we have to write it in its explicit formulation, because we actually have to know how to go from this prediction to the mean probability. And here we have to use the inverse logit, and this is how it's called in Stan. The function is called inverse logic, inv logit. So we can calculate the mean probability of occurrence as this linear model, and we transform it by the inv logit function. Here I did a for loop. Here we use the Bernoulli distribution. And the occurrence here is here specified as an integer. We need to specify this as an integer. And yeah, I use this for loop to calculate mean probability for each data point, and then saying, okay, the data point is Bernoulli distributed around this mean probability. But there is also, I think, in the practical, we see that there's also a nice vectorized form for this, where you can just write one line of code to automatically tell this to Stan how to compute this. Another classical model is ANCOVA type analysis. With that, I mean just that there's a categorical predictor. And here we have to code this in a specific way. So we just want to calculate or estimate what is the species richness at each landscape level. So basically we are fitting four intercepts here. So the deterministic part is depending on landscape. So this means we have 4 intercepts or 4 means here. You can dummy code this, but instead you don't have to dummy code this. You can directly kind of fit these 4 means. But for this, you have to code landscape as an integer variable, because then doesn't allow factorial predictors. So it's not possible in this environment to declare factorial predictors, but we can just call them or the levels, we can just code them as 1, 2, 3, 4. So landscape here will be an integer predictor with levels 1, 2, 3, 4, which correspond to agriculture, bauxite, forest, and urban. The reason why we are doing this is because we can use these as an index later in the model code. So here we specify, okay, there are n observations, there are m levels. We could also just, I mean, if we know it's 4, we could also just use 4 hard-coded in there, but here we leave it as part of the data. So we could also do this for different number of levels. Yeah, and then the landscape predictor is an array. So it's basically just a long vector where for each data point I specify if the landscape is 1, 2, 3, or 4. So each data point has its own predictor encoded as an integer. Then I will have here 4 parameters or m parameters, right? So each of them contains the specific intercept here. And then if I look through the data set, then I say, okay, each species richness in each location here, so for each data point, has a normal distribution with a mean where it's given by landscape of I. Right, so landscape I is a vector, and each landscape of I is either 1 or 2 or 3 or 4. So this is either B1, B of 1, B of 2, B of 3, or B of 4, depending on which kind of row in the data frame you're using. So we are just using landscape here as an index. This is how you work with categorical predictors in STAN. One last model. How can we transform this into a random effects model? So imagine for some reason, I now want to use landscape as a random effect here. So here we use it as a fixed effect. So we would fit all 4 of these independently, basically. Now we're using it as a random effect, meaning we want to estimate the overall mean while correcting for that they are that these data points are not independent but may be grouped in 4 of these groups. Okay, again, the deterministic part here is the same. The only thing we are changing is that now these B values do not have kind of a classical prior distribution with some fixed values. Now we leave these values as additional parameters. Okay, an array can be everything. It doesn't have to be a 2-dimensional array. Here is a 1-dimensional array. It's just the vector always contains continuous inputs. So all the elements of a vector can be 1.5, whatever. You can put integer values in the vector, but then Stan wouldn't recognize them as integers anymore. So you have to explicitly tell Stan that it has to be an integer, and this is done by the array. So the array of size n is basically the same as a vector of size n, but you can specify the data type which goes in there. So that's the reason why here we use an array instead of a vector, because we need later this landscape, we need this to be an integer, otherwise we couldn't use it like this here in the code. Same in the previous model. Here the response was an integer. I mean, it's 0 or 1, but we have to explicitly communicate that this is an integer by saying, okay, it's an array, so of just 1 dimension of size n. So basically it's a vector, but the contents are integer variables, because otherwise we couldn't use this variable occurrence here in this way for the discrete Bernoulli distribution. So for 2 specific reasons, we sometimes have to code this as an array. First of all, yeah, if the response actually is integer, in order to use this with this distribution, we have to code it. Or if we use a factorial predictor like landscape here, we encode it as integer, and we actually have to specify it here as an integer to use this as an index here, to choose which kind of B, B1, B2, or B3 is used as the intercept here. Okay, going back to the random effects model. Yeah, so here this is the classical ANOVA model, no random effects involved. All the B's here, so all the intercepts have their intercept. Here it's the same for all of them with some fixed values. You could also specify different values for them. They do not have to have the same prior. They can also have different priors. However, the prior itself has some constants here, right? So we put some numbers in there. In the random effects model, the only difference is that instead of having like actual values here, we say, okay, their joint mean, UB, and their joint standard deviation, SDV, are 3 parameters too, which are then estimated during the MCMC automatically. And we have to, or we should provide some priors for them. All right, so here the kind of the transition from the fixed effects models to the where landscape is the fixed effect to a model where landscape is the random effect is just that we replace these priors here by something where the joint mean and the joint standard deviation are free parameters as well. The rest of the code is totally the same. I mean, we have to specify these parameters here, and we have to specify some priors, but otherwise the model is identical. Okay, so these were kind of examples for a classical linear model, another classical linear model with a factorial predictor. We also had a generalized linear model, and then how to use this factorial predictor also as a random effect. And this is being done through the definition of the priors in these cases. Yeah, what else can we do with Stan? Theoretically, whenever you can write down something as a statistical model, you can translate this into Stan code. And whatever kind of model complexity or data complexity you theoretically could write all of this in Stan code. What else can you do? Yeah, sometimes you have models which have latent variables. These are pretty cool state space models, for instance. So latent variables can be defined. What I'm doing very often is process-based models. So where I don't have like a regression line or regression curve, but the predictions are actually generated by a small simulation model, by a deterministic simulation model. For instance, a population model, right? So, for instance, with time series data, where you don't have a regression line, but you have some some population trajectory over time, and you can fit these models as well. You can even do this if you have continuous dynamics. So Stan includes a continuous time differential equation solver. So I'm using this very often. I must admit it's a very specific problem, but for my line of work, I'm doing this very often. So classical, for instance, Lotka-Volterra or whatever, or just logistic growth or different forms of growth. You can kind of simulate this trajectory and fit this to the data. Some limitations. I mean, this kind of MCMC allows deterministic models only. This means there's no kind of stochastic simulation models. For instance, like you could also have like a stochastic population dynamics, where kind of whenever you run the model, it has some different dynamics because there's some randomness involved. This is not possible here. So deterministic models only. If the model has some non-smoothness, so if your kind of whatever complex response is not smooth, then Stan sometimes can have problems there. And also one drawback, which couple of models in ecology rely on discrete parameters, and this is usually not done in Stan. I mean, you can do this in Stan, but for these cases, I usually switch to Nimble because it is much easier in Nimble to have problems with discrete parameters. Yeah, and if you have a full spatial autocorrelation model, we talked about this yesterday already, this also can get slow, especially in Stan. If you have like, I don't know, 300 data points, this already gets annoying because it takes a long time to compute this. But there's alternatives, for instance, Nimble. The code is very similar to JAX, and I think it's replacing JAX nowadays, at least in the ecological community. It has been developed out of the ecological community by Perry-de-Valpine, especially for things like occupancy models, or models for estimating population abundances. The code itself looks a bit more slender and more readable because you do not have to declare all the variables there. And also the modeling paradigm is a bit different. So while stan is just a recipe where just the parameters go in and it just produces some output, here Nimble actually analyzes the code to check, okay, which are, all the elements, parameters, data are seen as nodes, and Nimble checks what are their connections. So the modeling paradigm is a bit different. There's a Nimble package, and you can easily specify code and so on. It comes with additional cool functions and tools if you have these classical ecological problems like occupancy models or these abundance estimation models. There you do not have to code all of this yourself. There's kind of functions for this already available in Nimble, which is pretty cool. And also, if you have some simulation model, for instance, something a model that simulates tree or forest growth. I know some examples where people use this and they come with like some stochasticity. Then you can't use stan anymore, but Nimble, among other choices, has functions for dealing with these random simulation models. Yeah, BRMS can translate a lot of models into stan code, but if you write it yourself, you can translate almost all statistical models into stan code. So it's not limited to the classical model classes. I personally use it for nonlinear models a lot. It all can be done in R. However, all these fancy tools in BRMS, they rely on kind of BRMS knowing the model structure and therefore being able to make predictions and so on and making model evaluation and so on. Since if you just have the raw stan code, we have to take care of this ourselves. But I must admit, it's not so bad. I mean, I'm always copying and pasting the same code for making predictions. So once you did this, it's not too bad using this for another model. Yeah, for complex models, sure. I mean, you have to do a lot of coding and so on, but there's a huge reference manual and also an active community. And I must say they're quite welcoming and friendly community in this forum. So don't be shy to ask some questions there if you run into problems with your stan code. Okay, here as literature, I just listed some. I think there's also 1 or 2 online courses and also some books which explicitly use stan for teaching statistics. Okay, so we are back after the break. I will just run through some classical models here. I think all of them basically we covered already in lecture, but I will show you in the code how to specifically work with them. I've written the stan code beforehand, so all the models here are I have available in the form of a .stan model. They are also available in the GitHub folder. So let's start with the first model here. This was our linear regression from the global plants data set. So let's look at the model here. That's basically the same as we have seen in the lecture already. So if we want to fit this model, we just have to provide a named list of the data, which has the same names as here, number of observation, predictor value, so latitude, and response value. This is log height. So we're putting this in a named list. And then we can already fit the model. So in brms, I always use the command or the specification backend cmd stan r. So this is a version of stan that is a bit faster. However, I'm not using this here because here we're using the rstan package to communicate with stan. And if I would use the other package, all this code here for communicating with stan would be completely different. So I'm using here the classical rstan commands here. However, the stan model itself is the same for all platforms. Okay, we can look at the output. The classical output, we get all kinds of quantiles, but we can also specify to just extract certain quantiles here. And if you want to extract these values, you can also kind of, instead of just having to copy and paste them, you can actually extract these values over the summary to have them in a table format. So you can extract them and have them here as a data frame, for instance. Yeah, you should look at model convergence. Here, rstan itself has some functions, but I like to use this one from the base plot package. For instance, the histogram or the trace plot here. And brms actually uses the same, so brms also calls the base plot package to produce these plots. Yeah, the MC-MC combo is exactly, I think, what brms uses. So we can extract the posterior as a matrix because that's basically what it is. It is just a collection of all the samples for all 3 parameters here in this case. And this is all we need for making predictions. So we want to make predictions for plotting. I define a range for the predictor values for which I want to draw the regression lines. And I call this xspread. And then I loop over all the posterior samples. So for each line, I'm making predictions for all these predictor values by specifying this matrix here. I initialize this as an empty matrix. So this is just an empty matrix with, yeah, here I think it has 100 columns because for 100 values of the predictor, we want to make the prediction. And then for each, we loop through all the posterior samples and we, it's the posterior. Sorry. So this is the posterior. So we're looping through all of them, meaning we're extracting the intercept at position I. So for instance, 1, 2, 3, 4, and the slope. And this calculates all these predictions. So we have for 100 predictor values, each of them has a distribution generated by 4,000 samples. Why doesn't it plot this? Okay, so we want to make predictions. We can start by drawing some regression lines. So here I'm choosing 1,000 samples. No, sorry, I'm not. I'm just choosing 50 random samples from the posterior and draw a regression line. But if we want to plot the whole distribution, we can extract the means and the quantiles here from this posterior, from this matrix of posterior predictions. So again, each column here contains all the predictions for one specific predictor value. So here the last one contains all the predictions here for this value of latitude. So we want to extract the column-wise means and the quantiles over the columns, and we can do this by applying the mean or the quantile over the whole matrix with this apply function. So here we are extracting the means and the quantiles, and I can use the polygon function to draw this polygon for the credible intervals with the lower and the upper 5% quantiles, and then add the mean prediction. So it's a bit of work, I must say, but you can always kind of copy and paste this and change it to your new problem. If you have multiple predictors involved, you can make different plots for different predictors. Be aware that kind of usually you should, if you have multiple predictors involved, you should, for the predictors which is not displayed, you have to choose some value, for instance, fix it to the mean value or to some specific level of this predictor. Then we can go through the same for loop, but now specifying that around this mean prediction value here, I want to draw a random data point. And I know that sigma here is the standard deviation, right? So I'm drawing from the normal distribution because that's the residual distribution. So instead of the fitted prediction, we are generating the, or instead of the fitted distribution, we are generating the prediction distribution. And again, we can extract means and quantiles. And here, these are actually the same commands here, just applied on this other on the prediction distribution now. I'm repeating this here for making predictions for the actual data points, right? So here I just chose a range of values for the predictor for which I want to make predictions, but I can also make them on the level of the actual observations in order to be able to compare observed and predicted. And here we are basically doing the same as before, but as predictor values, we just using the actual observations. And then this code is actually the same as before. But now we have this XSpread from which we can extract the means again, and then calculate residuals and plotting against the predicted values. And so the residuals here, also in the BRMS, usually, I mean, for each data point, you get a whole distribution of predictions, but we're only extracting the mean prediction, and therefore we're only displaying the mean residual here. Because otherwise, if you would display for, I don't know, hundreds of data points, also their distributions, the plot would be completely unreadable. The residuals plot included just the fitted distribution, but now we can also use the predicted distribution to make this posterior predictive check. So here we are plotting the density of the actual or the histogram of the actual response values of the data. And we can do the same for a specific, or actually for each draw of the posterior, we can generate a histogram of the predicted data. I'm just doing it for one now. let me do this again. Yeah, so this black line here, I don't know if you can see it. This is one predicted data set from one posterior sample. And so for each posterior sample, I have my intercept, I have my slope, I have my standard deviation. So I can make predictions for all the data points. And this is just the actual observation versus one predicted data set from the model. However, to make this a bit more informative, go back here, I can just say, okay, I want to predict 100 data sets from the model. This means I'm choosing 100 random lines in the posterior, and for each of them, I'm making I'm predicting a new data set, and then I'm comparing this to the actual data. So that's the same as the posterior predictive check, which is often used in BRMS as well. Here we see, okay, we can't reproduce this specific part of the data set. So potentially more predictors would have to be involved to get a better correspondence of the data and response here. The next example is a generalized linear model. Here, let's have a look at the data first. So it's this kind of data where we have some infection rates. So each of them was an experiment where a certain amount of mice was in contact with a certain dose of some parasite, and then the experiment counted how many of the initial mice were infected. So we are interested in the infection rate, or the mean probability, the mean infection rate, depending on the dose. So we would have a binomial regression here. So each data point here is like 5 out of 10 or like 15 out of 20. So we have this classical binomial regression. In the generalized linear model, we again have here a number of observations. The predictor here, this is dose. So dose itself is a continuous variable. But then we have this total number, and y is the actual number of infected, right? So if there's 15 out of 20 infected, then total would be 20 and y would be 15. Such where we can use a binomial distribution there. Here we have our parameters a and b. So this is some intercept and some slope. And we can, for instance, then for each of these, go back to this generalized linear model. Maybe I'm checking this generalized linear model in the lecture. I think it was here. Okay, so this is the logistic regression, not the binomial one, but I think it's fine for now. I mean, the model here is the same. So we know that so here, this is on the response scale. It's this S-shaped curve. And here is on the linear scale, it's this linear curve. So the link is the logit link. The logit link kind of transforms this S-shaped curve into the line. However, here we have to use the inverse, so the F. So this is the inf logit, the inverse logit that transforms this regression line into this S-shaped curve. All right, so here we have it in this implicit formulation. The logit of the infection rate is a linear equation, but we are transforming this. We have the infection rate is the inverse logit of this linear model. And this is what I'm doing here. So I'm looping through all the data points, and then I say the mean regression or the mean infection is inverse logit of this linear part of the model. and then the actual number of infected is binomial distributed around the total number and this mean. However, since this is such a classical model and it's so heavily used, often used, there's a kind of short form in BRMS where you can just use one line of code. It's the binomial logit. So you can just put all the y values here and say it's distributed as binomial logit with total is again the same as this, and then is your predictor and both of these parameters. So there's a there's a shortcut, there's a function already describing this this binomial logistic regression. Yeah. Otherwise, I mean, you can always kind of code this yourself by going through the classical steps of the generalized linear model. So this is the deterministic part, and this is the stochastic part. While this is compiling, I'm already going ahead a bit. This is all the same as before. So I have a predictor value which goes from minimum to maximum of the predictor value for which I want to generate predictions. Again, I specify this empty matrix, and then for each row of the posterior, I'm computing all the predictions here, again with the inverse logit function. Here's the intercept A and the slope B. So inverse logit function of this linear model uses this S-shaped curve, so produces all my predictions. Again, here you would have to like code this yourself. So for working in Stan, you actually have to know the mathematical formula of the model. So you actually have to write it down before in order to kind of code it later. So you don't have this this comfortable way of just describing family equal binomial. So here you would actually have to know the mathematical formula, how this model or what function has to be used in this model. Here, this, for instance, the inverse logic function. So let's quickly have a look here. Again, first of all, I'm choosing 50 lines randomly for drawing the spaghetti plot. Right, so each line of the posterior, each row of the posterior, I mean, generates one of these S-shaped curves. But I can also, from all of them, extract the means and the quantiles, and then use this to first plot the polygon, and then also the mean. In this binomial context, often the residuals themselves are not that meaningful. So we have learned that we can use the binned residuals plot, but we just have to extract the residuals, and then this binned residuals plot function automatically generates them for us. So I use all the predicted values for the data points and extract the mean, and then I can put them in this binned residuals plot. Right, so here we just predicted for all the data points this fitted value, extracted its mean. Okay, yeah, I have to scale it to the actual response, because this is just the so this predicted value is just the mean infection rate, and we have to multiply it by the total number of available mice to get the actual number of infected mice, and then we can specify residuals and then end up in the binned residuals plot. Okay, I think I'm quickly showing you one more model, and this is an ANOVA. Because here you actually have to code this, you have to code this predictor as an integer. I think I have shown you the model already. Yeah, so this is the Stan code. Yeah, maybe I show you the data first, and it's easier to understand what I'm doing in the code. Yeah, so we have species richness as a response, and we want to just run a classical ANOVA, meaning we are fitting 4 means. We can compare them later, or compare them to the to a reduced model to see if there are actual meaningful differences. We are not doing this now. I just want to show you how to technically code this in such a way that you can use it in Stan. Okay, we have a number of data points. We have 4 groups in total, right? So 4 landscape types, and then we have all the response values, and I can easily just transform the landscape variable into an integer. So this is the data frame. So we have the landscape predictor, which is here agriculture, forest, and so on. And I can easily just transform this into an integer. So as integer of landscape gives me, yeah, and encodes me the landscape level as an integer. So this can be used as a grouping variable here, or as a group is here the index in Stan. So y is the response. This can be continuous. However, here this has to be coded as an integer. So an array of size n, a one-dimensional array of size n, contains these values, which we can then later on use as indices, because here the parameters are, we have 4 intercepts, b1, b2, b3, b4. They can have a prior here. And then each data point is normally distributed around the specific group mean. And if we look through the data, we can use group to kind of always select the correct intercept. So because group is either one, depending on in which line you are, group will be either 1, 2, 3, or 4. This means that the mean here will either be b1, b2, b3, b4. So this can be used as an index to select the correct group mean for each data point. I've done this with a for loop here, but you can also do this in a vectorized form. So all of the data points, we can have this in this vectorized form, normally distributed B of group. This automatically generates a long vector where kind of each y gets their correct intercept. So this is a short way of basically saying this. So I'm waiting for the model to finish. So we are fitting basically 4 intercepts. The only trick here was that we have to kind of tell the model which data point gets which intercept, and we can do this by using the factorial predictor. We are encoding it as an integer predictor, which we can then use as an index. If you want to plot these predictions against the data here, we do not have to do predictions, or we do not have to compute the fitted values ourselves, because here the parameters are already the same as the fitted values. Right, so we are estimating 4 intercepts, so we can just extract these intercepts from the posterior. We don't have to compute predictions, because the parameters are already the predictions, or the fitted values at least. So here the output, we just fitted 4 means, and they are already given here. They're also summarized, so their means are already given. So this is B1, so the mean estimated species richness in agricultural landscapes. So here I'm just extracting them with a summary function. This will give me just a data frame where I can just extract the means and maybe also their quantiles for plotting them. And this is what I did here. I just plotted the raw data, and here I plotted points for the mean, and I used the line from the kind of lower quantile to the higher quantile to also display its uncertainty. Right, so here in this case, again, we do not have to compute the predictions. The parameters are already the intercepts. Here, so we can just extract them from the data, from the posterior. Okay, I think that's enough for now. You can check yourself if you want to, how you transform this into a mixed effects models. I mean, the code is already there. Here, the trick is just to replace these priors here by something where you have additional parameters for mean and standard deviation, which allows you to estimate an overall group mean, an overall mean where the random intercepts are given by these group-specific means. If you want to, for instance, make comparison between both of them, for instance, what is the difference between group 1 and group 2? Then you have to calculate this difference. I mean, here, I think it's pretty simple. I can easily do that. What is the posterior? Right, so I know, okay, this is my distribution of B1, that's my distribution of B2. So I can easily just calculate their difference and then look at the difference. So this would be post B1 minus post B2. So you would have to calculate everything you want to do yourself. And the cool thing about the EM-means package is that it automates all of these steps, but only if kind of the model structure is known. And here, all of the comparisons or all of the averages you're computing, you have to code them yourself from the posterior or from the predictions and so on. Yeah, that's just a bit tedious to do.